that's entirely enough of that. This is the Fixed Protocol channel. This is going to be a live practice run for my HFT presentation that is coming up just for you guys. It's also going to be on my trading investment banking technology channel, which is launching pretty soon. I am going in full for investment banking technology. Unfortunately, on this channel, I attracted a lot of people that are just tech interested, but not finance interested. So the finance stuff they're not interested in, so that kind of diluted my channel. That's how the algorithm works. It's horrible. So I'm gonna go all in and focus on people like myself, people that are in the industry, people who want to be in the industry, you want to get into financial technology, you're definitely going to want to subscribe to the new channel. But right now, this is a practice run for my presentation that I'm working on, which is going to go through high-speed trading technology, basically breaking it down. So let's get right into it. We got no time to waste. Let's get into it. High-frequency trading, what is it all about? So the fundamental parts of high-speed trading are, in terms of the architecture, it's all about maximizing efficiency, maximizing consistency, and obviously lowering latency as much as possible. You want ultra low latency. You don't want milliseconds, you want microseconds. So standard trading system is going to be in milliseconds in terms of the round trip. When we say round trip, we're talking about order generation all the way through execution. Order goes out, gets routed out, smart order router, algorithm, whatever it is, makes it to the trading venue or execution venue, and the execution flow right back. And you do that in, let's say, 1 to 10 or 1 to 100 microseconds. Let me give you the scale of what we're talking about. We're talking about 1,000, up to 1,000 times faster than a standard trading setup. That is the divide. Think about how many things that you know about that have that level of difference. Usually it's like 10x, 5 times more, or 10 times more, you know, maybe 100 times more, 1,000 times faster. So that is the world of high-speed trading. So I talked about consistency, which is a core part of high-frequency trading. What I mean by that is that basically it doesn't matter if you can go high speed for a short period of time. You got these bursts and you can just really fast standing out over, and then there's a kind of a slowdown, even a slight slowdown. Remember, we're talking about microseconds, right? So a millisecond delay or slowdown, that could be a massive problem, right? So you need to not only be fast, but you need to be consistently fast. How consistent? P99 percentile. There's a couple of percentiles that are used in high-speed trading architecture in terms of the design philosophy. P99 percentile basically means you set a metric of what the latency of the system is. Just how fast, quantify how fast the system is. And basically, in order for you to meet the P99 percentile, 99% of the time, your latency has to be at that metric or better, right? 99% of the time. So if you do a measurement every single second of the day, and you do a speed test, it should be as fast as that metric that you set for your system or better, right? So that's consistency. We don't have hardly any room for deviation. So that means only 1% of the time would your system be allowed to deviate from that metric of how fast you are. Now, it gets even more extreme than that. There's a P99.9 percentile. So what that means is same philosophy. 99.9% of the time, the system needs to be consistently this fast or better. Think about that, 99.9% of the time. That means you're talking about only 0.1% of the time that you're able to deviate from that metric. that is massive in terms of the levels of architecture and consistency and engineering to meet that. So that means basically P99.9 percentile applies to some kind of outlier. I don't even know how to scale that. I mean, it was like once every 3 months or something, you might have a deviation, you know, of lower than your metric of what your speed is. So that's core philosophy. And then, like I said, also efficiency. Everything needs to be efficient. It's all about customization. If you're into cars and motorcycles like I am, then you know no one just gets a motorcycle, fast motorcycle, and they race, or fast car and they race. It's all about customization. They're going to customize the car, turbocharged, supercharged, special tires, special suspension, and you might have a special trick about how you tune your car, how much air, how much fuel air mixture. Maybe you have a special fuel that you use. Whatever it is, highly customized. And when you go really, really high end, you're talking about, you know, NASCAR, Formula One. I mean, they might have a special compound they use on the tires that's like super grip or whatever it is. Same philosophy that we have in high frequency trading. Custom. And you want to squeeze out every ounce of power out of the system that you can, and everything that you need to do. Let me explain it this way. The philosophy of high frequency trading is basically, if we don't need it, we don't want it. Right? We're not interested in garbage collection, right? We're not interested in copying things from one location to the next. We're interested in productive work. So what is the system designed to do? What is it actually, what's its core function? An algorithm, its core function is to run the algorithm, right? The math, right? That's what we want to spend our time on, doing that math. If we're sending out an order, we want to focus on sending out the order. We're not interested in taking the scenic route and extra things. If it's not needed for the core task, we want to get rid of it, or we want to minimize it. Everything needs to be maximum efficiency. So let me talk about that in practical terms, what that actually looks like, right? So again, consistency, P99 percentile, 99% of the time, your system is as fast as your target metric in terms of your latency. And then you talk about, again, efficiency. Right? Everything needs to be the code that you use, the networking system that you use, the architecture of the servers, everything needs to be optimized. So let's first of all start with the client. So you're entering your orders, you have your pre-trade risk checks, right? Pre-trade risk checks need to be done in every single order. You're doing basket trading, you're sending out a whole bunch of orders. You want them to go out fast, right? You have a parent order that you send out. I want 1 million shares of something. It could be broken up into thousands of child orders or whatever it is, or you could be having tons of executions come back. The thing is, every single order that you enter, there needs to be a pre-trade risk check, right? You have things like buying power, right? You have certain risk metrics in terms of exposure levels based on sector, like maybe, you know, how much, so you have a portfolio, right? How much equities, how much options, how much futures, right? There's a lot of different metrics that you have. There's also fat finger checks. So for example, deviation from market price. If it's trading at $20 and you enter for $1,000, I mean, that should way trigger some kind of a metric that says, I mean, hey, or a risk check that says, I don't know about this. This is too far away from the market, so I'm gonna block this. I'm gonna reject it. Too far away from market price, right? Exceeding buying power. You know, whatever the rules are. So these checks, if you have a system that is super fast, operating in microseconds, and you need to do these checks on every single order, every single fill as it comes in, you need to do these checks on them, right? Because every fill is gonna change your position. If you're buying, right, now you have more of it. You have 100 more, 1,000 more, 1,500 more, 2,000 more, right? Every single one that comes in, you have to recalculate. Now your position is this, so how does that affect your risk, right? So these calculations have to be done super fast. How do you do that? The client enters the order goes to the server. It's written to your local logs. It's written to a database on a server, the order management server. So the order management server is going to, and this, again, everything's about fast, right? So as you're entering the order, I'm not waiting for you to finish that up. As you're entering the order, the minute that you enter a certain amount of details, we want to instantly start doing risk checks and certain assessments. We're going to check on the security master. Is this security tradable, right? A lot of different information, tick size, whatever it is. So we want to do that. We want to do risk checks. How do we do that super fast? A couple different things. We have the CPU, we have the GPU, and we have the FPGA card. So what is doing what? Basically, these components are doing whatever they're best at. There's a lot of different things that need to be done, different math that has to be done, different calculations that have to be done. What you will do in your programming in a high frequency trading application is you are going to write into your code basically what should go where, right? This goes through the FPGA cards, right? Your market data perhaps. Market data comes in very fast, a lot of bandwidth. You want that to be processed extremely fast. FPGA cards are really good for that. What's an FPGA card? Basically, you're talking about custom hardware. So the CPU, the problem with the CPU is it is a general purpose hardware component. It is not designed for trading, right? We don't design CPUs for trading. CPUs are capable of doing different types of logic, different types of calculations. So certainly we can tap into it and exploit it however we want to, but we are limited by this general purpose device. Just like in automotive racing, you want custom. So the next step is you use the GPU. Why are you using the GPU? GPUs are really good at parallel processing, right? They're really good at processing and doing a lot of calculations in parallel really fast. So we delegate some tasks to the processor. You have a multi-core server, right? So obviously it's multi-threaded, so you have multiple threads running that are doing different calculations. Some of these tasks are delegated to the GPU to do some of the calculations. And then the FPGA card, what is that? Basically, you have a CPU, general purpose, not designed specifically for trading. You have a GPU, same thing, general device. This is not for specifically for trading. Then you have the FPGA card. You have custom, think of it as a custom processing hardware. So just like how the CPU and the GPU has certain logic that is built into the chip itself, actual hardware, right? You can program your own chip or processor in the form of this FPGA card. So your firm has custom logic or risk checks or whatever it is that you're doing that's your own custom thing. You can actually program the FPGA card to do those things. So now you have hardware that is specifically designed to do whatever it is that you need to be done, whatever the calculations are. So it's going to do it at a tremendous speed that is going to outpace the CPU, outpace the GPU. But ultimately, remember, it's all about delegation, right? It's not that we're going to use the FPGA card. No, it is a coordinated effort between the CPU, GPU, and the FPGA card. So those are some of the main components. Now let's jump into networking. So how do you transmit those orders at the speeds that we see in high frequency trading? Again, in microseconds, not milliseconds, 1,000 times faster than standard trading. How do we pull that off? Network obviously needs to be highly optimized. So we're using specialized network interface cards. So your network card that is in that trade server is a specialized card that supports a technology called kernel bypass. Remember we talked about maximum efficiency. We don't have time for nonsense. We don't have time for garbage collection. We don't have time. I mean, obviously we have time for it, but you know what I mean. You want to focus a majority of your time on productive work, right? Anything that's not needed, get rid of it. So with kernel bypass, what's happening is basically the network card says to the operating system, listen, man, when those packets come in, I know you like to do your thing about making sure the data is, data integrity is good, and what I don't even know what you do. Well, I shouldn't say that because we're taking over some of that work, but basically not interested. The operating system, even though in a trade server, it would be highly optimized, you're going to use something like a Unix or Linux server. So you're going to have it be very, very lightweight in terms of we only have within that operating system, we only install what is needed for trading and nothing else, right? But we have a same kind of principle with the networking itself. This network card has a kernel bypass. So basically what's happening is, instead of the packets coming in and then they go to the kernel to say, hi, what's up, how you doing, I'm a fresh execution coming in at IBM, right? We don't have time for that. We are VIP, right? We want those executions to go straight to the trading application, direct, shortcut. So we bypass the kernel. So one of the principles here that kind of applies is something called zero copy. Zero copy is basically what it sounds like. We don't want to be copying from buffer to buffer to buffer. Every time you're copying data from one location to the next, that introduces latency. So we don't want to go to the kernel bypass. I mean, we want to go to the kernel and then have it go from this buffer to that buffer and this check and that check. No. It hits the NIC and it goes straight to user space, straight to the application, basically. So the trading application is going to run in a process being a grouping of resources that the application needs. So part of that process will be memory allocated for the application. This data can go straight to that space and be available for the trading application, and that is much faster than, again, going to the kernel. So kernel bypass network card going straight to the application. Now, here's another thing, a core part of the architecture on the server level. So you have something called UMA and you have NUMA. So UMA is uniform memory access, and NUMA is, I keep saying UMA. It's not uniform memory access. It is UMA and NUMA, not UMA. Non-uniform memory access. So what's that all about? We have a bottleneck. And potential bottlenecks. It's all about bottlenecks. In high frequency trading, it's all about avoiding the bottlenecks. We got to find out what are the bottlenecks in our architecture, and we mitigate them as much as we can. One of the bottlenecks is in a multi-core processor. You have, and this is also another core principle of high frequency trading, is proximity, right? The distance from the data to the processor is something that it takes time, right? We're trading at the speed of light, right? If you have a processor here and you have memory here that the processor is processing, that is the ultimate, as opposed to, let's say this is the processor and this is the memory location. The further the distance that the data has to travel to the processor, the more latency. Again, in a normal situation, I'm not even going to say normal trading, because any trading is going to be very latency sensitive. Let's just say a normal application. In a normal application, unless it's like some kind of gaming, it's high-end gaming, we normally aren't concerned about the distance of the memory to the core. Like, who cares? When you're operating in microseconds, we care a lot. We want the data to be as close to the processor as possible. So what do? NUMA architecture is all about basically a grouping of cores and memory. So you have multiple cores in your processor, and each core has some memory that is in close proximity to it. So imagine you have core and memory, right? So a really short distance. So you have this data that needs to be processed. It is in that memory that is close to the core, and then the distance is really close, so you do the processing really, really fast, right? And the other advantage is with UMA, the bottleneck, a big bottleneck, which gets worse as the more cores, as you scale to more cores, it gets worse, is something called resource contention. Resource contention is basically fighting over, like, remember, like when you were a kid, I want to play with it, right? So everybody wants to play with the cores, right? But the problem is you are going through a shared bus with UMA, right? So you have all these cores that are trying to, basically data is transmitting between that core and memory, going through a shared bus. So resource contention is this bottleneck of, think of it like a traffic jam, right? With NUMA architecture, you avoid that by, again, grouping the memory and the processor cores, so you don't have that resource contention. Again, you want to squeeze every ounce of performance out of that system. So kernel bypass on the network, NUMA architecture, utilizing multiple processors, the CPU, the GPU, and the FPGA card. Now, what is our path to the exchange to get our fills? Now, there's a lot of other steps I'm going to skip for now, but basically imagine order management server connecting to a algo server, connecting to a smart order router making a decision to go to a particular exchange. Let's say it's going to NYSE. What does that connection look like? DMA, direct market access. We're not going through a hub and spoke network. We don't have time for delays, right? We don't have time for going to this network and then they're going to route me to, no. We want DMA, a direct lease line that goes straight to the exchange, right? But here is another really big factor in how we get high frequency trading architecture, how it works. Something called co-location. Where is the algo server located? Where is I would say the algo server itself co-located on the exchange floor itself. So what's happening is you have your algo server or your trade servers located in the same data center as the exchange servers, connected via a cross-connect cable. So basically, you have, again, remember I said proximity with the NUMA architecture. You have the data really close to the processor, right? And another thing I didn't mention is that you try to really maximize this architecture through the way the application is written. There are ways that you can write an application that you keep the data that you need, that you most frequently access in your cache, right? In your cache, you're going to have the fastest time in terms of response times, right? So if there's data that you're accessing on a regular basis, a lot, right? You would like that most times when that data is requested, it happens to be in that cache, because you know that cache is fast, right? So that's going to maximize the performance if you write the application in a way that certain functions are cache friendly, right? So now we go back to the co-location. So you have the server at the same data center as the exchange connected via cross-connect cable. Every client has the same exact length of cable. This is the way that you normalize for all clients, right? Because again, we're operating at the speed of light. If one client has a cable that is slightly longer than the other, the speed at which the trading occurs in high frequency trading, I mean, you could be thousands and thousands of transactions per second, right? When you're operating at that speed in microseconds, the distance of the cable makes a big deal. A client that has even, I don't know, let's just say 3 feet shorter cable can have a competitive advantage because, again, speed of light, right? Those packets are traveling a shorter distance, so they will take less time. And immediately, not necessarily, might not be that big of a deal, but over time, right? If you have this small latency, scale that over the trading day, what that can mean in terms of lost revenue. So every client, same length of cable. You're closest to the server, doesn't matter. Your cable length, same length as the person furthest away in that data center from the server that you're connecting to. Obviously, in the way you route the cable, getting too much in the hardware here, I don't know how exactly they wrap it, but you have to consider electromagnetic resistance. As you know, when you coil a cable and you put a signal through it, that can introduce a magnetic signal, so that can potentially affect the performance. So I don't know what the techniques are. I'm not a networking guy, but I'm aware that that is a thing. You don't just wrap it up somewhere in a circle. I'm sure there's techniques that they utilize, but this is how it's done. This is how you do it. You locate your trading server on the exchange and you have this really short distance. Now, I want you to understand the importance of this. I mean, I think you can understand, well, oh, okay, yeah, the server is really close to the exchange server, so obviously that's faster because of the distance. Yeah, I get it. But do you really get it, right? There's another component. There's this whole thing, a metric of the round trip, right? You send the order out, it goes to the systems, it goes to the exchange, right? The exchange fills the order, the fills come back to you. Consider these two options, right? you host your algo server in your data center. Let's say you have a data center in Secaucus, for example. So you have your algo server in the data center, right? That algo server needs market data. It's acting on the market movement, right? So obviously, if you're going to operate in microseconds, right, you need a feed that is that fast, right? So the thing about it is, if you are sending market data from, because the executions are happening on exchange, right? So, you have an execution that happens on the exchange. That market data needs to travel all the way from the exchange to Secaucus, right? So you have latency right there. You're waiting for this market data to make it all the way to Secaucus. In contrast, the high frequency trading guy has his market data feed right on the exchange floor, his trade server right on the exchange floor. So he's already got that update, right? So the high frequency guy has that update of the price movement. Their algo server sees this price movement and based on the logic makes a decision that this is an opportunity to buy. So they enter the order to buy, right? Send it out to the exchange, get the executions. Perhaps in that same time frame, you're just now receiving your price update. So the high frequency guy got the market data change, right? Generated an order, got filled, right? And he's done. You are just now you have to realize the science of this, right? You're always operating in the past tense, right? As fast as trading is, this is not an actual real-time thing. Things have to happen in sequence, right? And you could get into atomic clocks and all that. We're not going to get into this one here. But things happen in sequence, right? The execution must happen first in order for that signal to be transmitted to people that are subscribed to market data to see this event, right? So everyone, even the high frequency trading guy, is operating in the past, right? They're responding to an execution that happened in the past, right? But the problem is the guy who's getting his market data from Secaucus, he's even further in the past, right? The guy that's in an exchange floor, yes, there's a little bit of a latency between execution and him getting it. Very, very small latency, but it's much shorter than the guy who is in Secaucus. But let's go through this full process, right? Market data goes from the exchange all the way up to Secaucus, where your market data feed is, right? Your trade server or algo server is subscribed to that feed. So you see this price change. Your algo server decides also that this is a buy opportunity. Now, keep in mind, the high frequency guy already got his fills already. And you're just now saying, hey, man, let's send a buy order. You're just sending a buy order. They're already filled. So you generate a buy order in Secaucus. So you had the time for the market data to go up to Secaucus. Time for this does take time. It's really fast, but it does take time. Your algo server needs to do the calculation, right? Based on your position, based on whatever the math that you set it up to do. It says, oh, this is a buy signal. I'm gonna buy. It needs to generate the order, and then now you need to transmit the order from Secaucus down to the exchange. So you're losing time of the market data going up to Secaucus, and then your algo server generating the order. Now you're wasting time waiting for this order to go down to the exchange, and now the exchange gets your order, and then they fill your order. Then you're waiting for the fill to come all the way up to Secaucus. This is an eternity, right? This is an eternity. You're always going to be behind, right? The high frequency guy is going to be able to get certain opportunities that you're not going to be able to get because of all this latency. Now, remember, with the guy that has his servers co-located, it's like he's closer to real time. The minute that an execution happens, or the microsecond that an execution happens, you're able to get that feed data to your server to see, oh, opportunity to trade. Send the order out, fills come back. Everything is just like, brr, done. Right? But when you're in Secaucus, it's not done. It's, oh, market data. Got the market data. Oh, this is a good buy thing. Send the order down. Okay, the order's going down. Okay. Hey, order's filled. Oh, okay, the fill's coming up. Fill's going up. Okay, I got filled. Right? While you're doing that, maybe there was another opportunity. There could have been 3 or 4 opportunities that happened in the time that you're waiting for things going back and forth, right? Those round trips going up and down from Secaucus down to the exchanges, that is no good for high frequency trading, right? That's why you do the co-location. So you basically have the server that is making the decision on when to buy and when to sell is as close as possible to the trading activity itself. That is the sort of the impetus for trade action, whether it's a buy or a sell, right? So you're eliminating this up and down stuff. So I think we covered most of the core things. I guess I could touch on some of the programming architecture as well. So as far as the programming goes, and you guys have any questions, let me know. As far as the programming goes, like I said, you want to spend most of the time on actions that are productive, right? So with the algo server, I want the algo server to focus on actual what's the word? The actual calculations, right? So I mentioned garbage collection. Now, the way that you would design your application is you would pre-allocate memory, and it depends on what task we're talking about in the application. Well, let's say you have something that is doing parsing, right? So you would want to pre-allocate memory that would be sufficient for 75 to 85% of your data structures, however you're storing this data, right? The idea is that 75, 85% of the time, when you create a whatever it is, dictionary, whatever the data structure is, every time you create it, memory has to be allocated for it, right? But if you pre-allocate the memory, and the memory size that you pre-allocate suits 85% of the executions, then, or the data rather, the input data, then that means in most cases, you don't have to do the resizing, right? Because let's say, for example, you're parsing something that is larger than the space available. Now the application needs to request from the operating system that I need more space, so allocate more space so I can store this bigger line. Those are the garbage collection pauses, right? So your application has to wait in this time frame of requesting more space, resizing. Again, when you're operating in microseconds, for normal application, probably don't care about stuff like this, right? High frequency trading, we care, right? The time that it takes for this request and a response, we don't want to do that. So we want to make it so that most cases we don't need to resize, right? And I'll go into much more details in the full presentation, but this is just sort of a basic summary. And like I said, this is just a practice run for an upcoming presentation I'm going to be doing, which is going to be much more thorough, and I'll have my diagrams. I'll be on the light board and everything. And if need be, I'll put on my gas mask for theatrics. No, I'm not going to put on. All right, guys. I got to go get some paint. Some touch-up paint. And it's just raining all day today, man. This is Carlyle Speaks Wall Street, and that has been a presentation about high-frequency trading architecture. Stay tuned for the full presentation coming up soon. And also, like I said, I'm going to be also I'm also launching a new channel which is dedicated to investment banking technology. So I know some of you guys subscribe just for some of the technology content, like the SQL. A lot of you guys subscribe for the SQL content, but you're not into finance, and that's bad for the algorithm. So I want to dedicate this channel to people in my industry or people who want to get into my industry. So it's going to be all investment banking and technology. And there you have it. Now let me go get my paint. If you're just joining, go ahead and click on the like button, subscribe. And until next time, this is Carl Speaks Wall Street. See you soon. Oh man, I'm gonna get a strike because of this music in here. I'm out.